Today we are going to study about density of states of a quantum dot, or quantum dots are also called artificial atoms and zero-dimensional materials. So if a material is such that the length and width and height of the material is of the order of de Broglie wavelength of the electron, then such a material is known as a quantum dot. So in such a case, you see that energy will be given by h bar square k square upon 2m, where we are using the effective mass of the electron because the electron is not completely free but it is inside a lattice. So a k vector will be discrete in all the three directions. So we replace each k by n pi upon l. This we have discussed many times already. So it means that the energy is not continuous in any direction. The k vector is not continuous in any direction, due to which the density of states for such material is given by a delta function. So and this vector of 2 is written here because of the two spin pairs of the electron. While it means that whenever E will be equal to En, the density of space states will show a spike. But in although ideally it should be of infinitesimal thickness, but in actual it will have some FWHM, some width, and the peak will have some width because of the collisions of the electrons in the material with the lattice and dots and defects and etc. And this luminescence also the quantum dots show a very narrow luminescence because of these because it doesn't have any continuum of states, and because of which it can be used in lasers, biological markers, and as charge islands in Coulomb blockade and so on. So if we compare density of states in the three materials, in the three-dimensional material, two-dimensional material, you see in a three-dimensional material it had 1 upon E minus. It was depending upon E minus EC under root, and then it was a step function for a two-dimensional material, while for a one-dimensional material, which is shown in green, it was a mix of a delta function and a continuum of states. While in a zero-dimensional material, you just have delta functions and you just have these spikes at particular energy values. So we have been talking about a particular band here. So if this was about an electron in the conduction band, then the density of states in the valence band can also be found in a similar manner by instead of talking about the electron, if we talk about the hole. So if we draw a similar band structure for a valence band also, for it means for the hole. So you see that this blue line is because of the three-dimensional material. So for a bulk material, this will be the band gap EC minus EV. But for a two-dimensional material, the band gap will increase, which is shown in red. While for a one-dimensional material, it will increase further, and the band gap will increase much more in case of a zero-dimensional material. Much more confinement is observed in a zero-dimensional material. So quantum dots are also called artificial atoms, but they are not actually atoms, but because they have discrete states, and that is why we call it as artificial atoms.